Okay, good morning. We will now look at different kind of elements. To begin with, we will look at the rectangular element. Yeah. So as such, we are already chapter 6 plus 7 plus 8. We are going in parallel so that we understand basically. So we take one kind of element, we complete it. So you know how they are connected. If you see now you can understand. Chapter 6 is all about the weak formulation from a strong form to weak form. This is about the types of elements, how you formulate the test functions, and it is how you solve it. Now we have done already for the triangular element. Yeah. Okay, so now we are moving to four noded elements, and it's easy only. What we have to do in this case is main thing is the how to find out the stiffness matrix. All others you will use the same method. I mean, all are basically whatever we have done for triangular, we will just repeat it for the rectangular element. So let us say you can do any way. You can also have 0, 0, A0. Node 1, node 2, node 3, node 4. Always you start with node numbering. You have that. Then you have AB. Then you have 0B. And based on that, you can find out the what should be the stiffness matrix for this. Yeah. And for that, you start with the problem. Big formulation, as you know, you can relate it to the 1D problem, right? See, in 1D, like you have similar it has. So you start with, you know that this will be W Q dot N D gamma, and this is for the whole boundary. Yeah. So if this element at the boundary, then you have to calculate this one. If it is not at the boundary, then this will not be there. So because internal, like what I mean to say is, if you are taking this field from here, there is no boundary here. So this term will be anyway 0. But if you have one element which is here, then there will be a boundary here. So accordingly, you have to that will be relevant in that. So as you know, so typically you write like this one. And as I told earlier, this is what is this? This is a heat loss. Right? See, this is the heat loss. So we have minus we write, and here we have the gradient of W dot Q and d omega over omega. Okay, then we also have a minus here as well, because this is all we are talking about heat loss only. So S is the heat gain term. So here, hence you will have it Wxy, Sxy, and d omega, and over the omega total will be equal to 0. So this is what we have, and regardless of what kind of element you have, you will end up with this goes to force, like this becomes this gives rise to a force. Basically, this one is a stiffness matrix. Stiffness matrix multiplied by temperature vector in this case, or force vector, force vector, and this also gives you the force. Right. Now, in this case, also like as we have done earlier, this may have convective heat transfer term. So in that case, it may also have the stiffness. It may also contribute to a stiffness if there is a heat convection or wear convection. So this we have, in general, we have seen that, right? Okay. Then main thing is this one from where we get the stiffness matrix. Yeah, so all others we know you can work the same way. It's only varies is number of nodes. So hence this term in general, if you see W dot Q d omega, this term finally will be WT, yeah, and then you will have B transpose dB, right? Then d omega over omega, and then you will have a T. So all these are matrices. So finally you will have in this form. What dB? dB, then this will be as K11, K12, K21, K22. So this is an isotropic material. Otherwise, this will be equal to K1001 for isotropic material. So all this repeating. So we have done already. So basically we can also write this as this we have done already. B transpose B d omega K here. It will be, or if K is constant, or even if K is varying, and if it isotropic, may be isotropic but not homogeneous, right? So homogeneous meaning that it's not the same value everywhere. In that case, K may be function of x, y, and hence it will be inside the integral. So this we have done already. We know that this is how it varies. Finally, it comes. This one is equal to, we can write as transpose this K, right? Okay, here also we have. So this will be K and then T for temperature vector. So we have like this one where we know that K will be equal to BT dB in general, or is equal to K BT B d omega. So this is an isotropic. In general, you can make, but this is for isotropic. Like that. So this just we are repeating because this will repeat again and again. Only thing is the definition of B will change. If it is 3-noded, it will have 2 by 3, right? 2 by 3 matrix. So for a triangular, you have a 2 by 3 matrix of B, and remember this will be del n1 over del x, del n2 over del x, del n3 over del x, right? And del n1 over del y, del n2 over del y, del n3 over del y. Then you have the 4-noded. This will be simply, so if you have 4-noded, then it will have this is B, it will be 2 by 4, and this will be n1 over del x, del n2 over del x, del n3 over del x, del n4 over del x, del n1 over del y, del n2 over del y, del n3 over del y, del n4 over del y. So this will be the only difference, and it depends on the number of nodes. So this is 2 will be always true. This is number of nodes. So if you have 5-noded, you will have 2 by 5. You have 6-noded, you will have 2 by 6, and so on. Right? That's the thing. So in general, you can write that B will be 2 times n, where n is number of nodes. In general, that's it. And then only thing remains now, how to formulate n1, n2, n3, and so on. That's the only deal remains. And that's what we will be focusing on, right? So we will not focus on now, we will not go back to all the details. You know already how to Then only thing is we have to focus on how to find out the stiffness matrix. That's the main thing. Yeah. So we will focus on that one. Any question, guys? Those online?
No, sir.
So I'm going to delete here. I will just have so we will start with N1, N2, N3, N4, and we will derive, we will go to B, and we can find out what the value of K. That's what we are going to do. That's it. Okay, not more than that. Rest you can do. Rest it is very easy to do. Yeah? Rest even if you have S, then you have S, right? S times W, and now you know W will have 4 N's now, right? So you can have 4 forces. That's it. So this remains the same. Nothing different. Okay. Now here we will have N1 xy, right? So we know that this is x, this is y. Again, formulation is up to you how you want to formulate. It's possible that you could have your the origin here as well. Right? It's possible to have that way also. So not necessarily you have to do here. Right? It's not like that. We are just doing it. It's up to you, like how you formulate. It's and we will see later on also, how in the middle actually helps. So that is also there, especially the but we will right now. Let's go as per this one and see how it works. So N1, as you know that we are talking about this one. We know that here everything has to be 0, here everything has to be 0, and simply you can write it as this one is as x equal to a, x minus a, and this one is y minus a. Either you can write like this one and then you say alpha and you do it, or you as we did yesterday, right? So you can also write a ready-made thing. And in this case, it will work, and that is you will have from here to here, so it will be 1 minus x over a multiplied by this, so it will be 1 minus y over b. So this will also work. Here you don't have to scale, right? See, it's already there. Yeah, so you put if you put value x equal to 0, y equal to 0 equal to 1 already. It's already a scale. What we have done? 1d this side, 1d that side. We multiplied, you get it. But not always the good thing to do. Here it is a good thing because this is rectangular, but let us say if you have this triangle, right, and you do the same thing, we have seen that we have just bilinear, actually this is called bilinear, say 1x plus y, so alpha y, this is my planar, this is a equation of a plane, right? So here one planar equation can actually do it, but if you do the same thing you apply, you end up with bilinear form. Not necessarily is a good thing, right? So still you will be able to do it, but actually this will give you different results. So typically what you do, you want to have the order the minimum possible, so that way it is better. Otherwise even the solution may not be guaranteed that what you want to get and so on. So typically that's why for this one you never use this kind of equation. For this you use the planar. Right? Anyway, so you have this one, and similarly you can write N2 xy. So for this one, and then you know that in x direction you have gone to number 2. So you will have x over a in this direction, and this direction still you have. So you should write like that. N3xy. Okay, so here we have both the sides we have gone to number 2 ones. Right? So x over a, y over b, then N4 xy is equal to, here we have, well, this is the first one is x minus a, the other one is a. So we have like this. And now what you have to do, you have to make the this is n you got, we have to make the B matrix, and hence we have to start differentiating, right? So n1 over x, and then you will get minus 1 over a, 1 minus y b, right? And so on, right? So then n1 y is equal to, you get 1 minus x over a multiplied by minus 1 over b. Yeah. Similarly, we get del n2x is equal to, so you get 1 over a, 1 minus y minus b. Del n2y will be equal to x over a minus 1 over b. Del n3x, del n3 del x is equal to minus 1 over a, y over b. Oh, sorry.
आपने खासा खैरियत का मिला है.
Okay, and del n3
बस अभी आ रही.
y is equal to
देखने आई थी पति की प्रोग्रेस रिपोर्ट.
del n4 del x is equal to minus 1 over a, y over b. Del n4 over del y is equal to 1 minus x over a, 1 over b. Okay. And rest, you know that b, how we can compose. B will be equal to del, so if I let it there, b is like this. So we know that we just repeat it here just for continuity. So that x1, n1, x, n2, x, n3, x, n4, x, n1 y, n2 y, n y, n4 y. So we have this, and from that we can easily find out k11, k12, and so on. So a few we can compose basically. You also know that here the stiffness matrix will be symmetric, so that also you can take advantage of that. So K will be what? K, let's say, assume isotropic material. Isotropic. Yeah. So in that case, K will be equal to, right, a small k, isotropic, and k equal to constant. It's not time, meaning that isotropic homogeneous. Also you write homogeneous. So typically when you work with some commercial software like Abacus and all, they will ask you what kind of material you want, right? So isotropic homogeneous material. Yeah. So otherwise you say inhomogeneous means k is varied, and in that case you have to define. You have to define the reason here k is different, reason here k is different, and so on. When k is a function of x, y, then you have to write a subroutine, right? You have some, typically you have Fortran or subroutine or Python or so on. Sanjay, you find out whether students can have access to abacus and all in our lab. Okay. So that if you guys want, you can have hands-on experience or some software, some abacus and scissors. So today only just find out. Tomorrow we can announce. Now that you guys are here, so you can also go to the lab. You can play with some software. You can. So K, VTB, B transpose B, and that really means homogeneous. That is K equal to actual, that is K equal to constant, and K equal to like this, and then is equal to K VTB. What is the size of K? What is the size of K? V is 2 by 4. So P transpose is 4 by 2. Right? So 4 by 2 is this. So this is 2 by 4. So 4 by 4. So K becomes 4 by 2. In general, you know already. If the number of nodes 4 becomes 4 by 4. Number of nodes 5 by 5. But only for the scalar field problem. Then we have displacements, then things will be different. We will have displacement exactly and direction. Then it will be twice. We will see later on. We go to chapter 9. Yeah? Chapter 9 we have for plates, we have the elasticity problem coming there. Any questions so far? There. So, in general, you can also see now when you multiply V is equal to, let's see here. So, in general, you write del N1, del X, del N2. So, transpose of that, so let's write transpose to begin with. So, del N1 over del X, del N2 over del X, del N3 over del X. Del N4 over del X.
मैं यहाँ पे पैर नीचे करो
I del N3 del Y
गलती आ जाएगी ना ब्लड गिरेगा तो
del Y del N4 del Y. And then you have del N1 del X, del N2 del X, del N3 del X, del N4 del X, del N1 del Y, del N2 del Y, del N3 del N4. Okay, and you can see here how it multiplies. So 1, 1 is the first one multiplies how? We go like this and like this. So this is square plus this is square. So K11, that really means what? K11, which is a member of this K, right? Or simply you can write Kij. So let's say ith is from here. I is, let us say, I equal to 2 and j equal to 4, right? So I equal to 2 is here and j equal to 4, 1, 2, 3, 4 is here. What do you get? You get this multiplied by this. So what you get in that case is A and then del Ni over del X multiplied by del Nj over del X plus del N del I over del Y del Nj over del Y. So we get simply that. You know that Kij, find out like that. In general, you write like that, and in particular, you can find out K11, for example. K11 will be equal to K, then this will be equal to del n1 del x square plus del n2 over del y square. Over whole domain. Or here, just we will have this as one example, and rest you know that you repeat the same thing. You can. Main thing is the understanding the process, because this is for computer applications. Right? Finally, it has to be implemented on computer. That you should know. Manually, it's not possible that you do everything. Rest you can use the methods you can use to compute. Yeah. So yeah, encouraged to do it. Like you can use Mathematica, for example. So from there you can see in Mathematica what happens. You can see how you get expressions and the values and all. So, yeah. Okay. So K11 we can find out. We can just find out one. That's it. So this is K, and then we have N1. Here is that here. So minus 1 over A and 1 minus y over B. So we get this square and this square. We have to add them. Right, so we get 1 over A square, just like that. Then 1 minus y over B square, okay, plus. So the square of this 1 over A square, 1 minus y over B square. Similarly here, 1 minus x over A square and 1 over B square. Okay, and this is equal to what? This is equal to, okay, Gauss quadrature you can apply here also. That will be take up later on. But right now, let's say we have to just integrate. So what you get from here is you will have a double integral. And since this is the rectangular domain, so it's very easy to form that way. So you can write K, get a 0 to x, 0 to y, 0 to A, and 0 to B. And then you have K, and then 1 over A square, 1 minus y over B square, plus 1 minus x minus A square, 1 over B square. So you will have dx dy. Dx and dy is equal to, now it is actually separated. So you can see here that straight away you can find out K times, for first one, only y is actually applicable, x is not applicable. So you can actually write K 0 to A dx, 0 to B, right? So in first one, we can have even A square outside. So we wrote A square here. And in first one, there is no x term. So x term has 1 coming here. And the rest, we will have 1 minus y over B square. Dy. Right? It's fine. Second one, accordingly, plus you have a K over B square. And then you have 0 to B. And you have dy, and then you have 0 to A, and 1 minus x over A square dx. And that is equal to, you will have, here you will have K A over A square, you get A from here, and from here, what do you get? You get 1 minus y over b cube over 3, right? divided by minus 1 over b. Right? So this b0 plus k over b square, we have b, so write b here, and we will write the same way here, and which will be 1 minus x over a q of that divided by minus divided by 3 divided by minus 1 over a, and we have b to 0. Right? And is equal to, you can find out from here that a over a, and if you have b here, that makes it 0, right? So first term will be 0, the second term will be that, right? So you get is equal to, and minus becomes plus, yeah? So that becomes b over 3, that is this one minus plus, and then you have 1 over so b0, 1 over bq, right? Is that correct? So b0 minus bq only, no? bq होगा ना? Oh, अच्छा 0, so no bq का. It will be just 1. Anyway, it's a squirrel, so it should not come. Okay. Fine. And then similarly, you get plus a over b, and then you have a over 3 and minus a. Right? So it is equal to k b over 3a plus k a over 3b. So that you get the answer. So it's simply equal to k over 3, and then you get a over b plus b over a. And this you can extend to a square element, right? In that case, a will be equal to b and n. So any question, guys, from here? And so on. Yeah, so this is the method you do. In software, what happens is typically you choose the type of element, and automatically it knows at background there is a matrix given. Okay. Based on the parameter, what will the value? You just put a equal, replaces a with whatever the value it gets. So it's not that they start from the weak formulation. No, so those things are already set already. You know, so and the moment you define when you mesh it, and then if you say you have chosen a rectangular element, then what it will do? It will find out what is the value of A, what is the value of B. I mean, what is this width, what is the height of that. Accordingly, it will build the stiffness matrix. That's what it does. So this formula will be already fed up somewhere. But when you have a few things varying, so if you want to define your own things like the thickness value varying, so then you have it has to integrate them. Then it will do all the integration. Yeah, and integration is done numerically, as you know that house, and you can also apply it here basically. So that we will take up later on. Okay. Now, only thing now remains is not necessarily all the meshing that you do is a rectangular. Yeah. So there could be irregular shape. Yeah. And then what do you do? That's the thing. Yeah. So there is something called isoparametric alignment. We just introduce and we'll see how much we can cover today. So we just have 15 minutes around. So we have irregular element. It's called isoparametric elements. This will be irregular, so you write 1, 2, 3, and 4. You have x1, y1, x2, y2, x3, y3, and x4, y4. Like that. Yeah. Okay. There is a relationship between, if you want to do this one, first thing you will need to convert it into something you know to begin with, right? So this is a coordinate transformation you do. So yeah. And what you want to do, basically this looks like something like this. Yeah. And where you have this xi and eta system. So what you have done, we have converted from irregular quadrilateral element. Yeah. So in fact, this is what you call a quadrilateral element. Still, you can solve this one, right? You can still solve. How you solve? Instead of converting to this system, you can also still solve it. How will you do it? Not triangular. It's not allowed. Means you have to use the quadrilateral element only. But if you change to triangular, what happens? Tell me. Why you would not do it? Triangular element has problem. What is the problem? Problem is it varies linearly, right? So its order is limited, right? It has planar basically. Alpha plus beta x plus gamma y. If you quadrilateral, at least you will have a higher order, right? One order high. This is better. So that's why you will not change it. It's better to use this one. But what you will do, you will assume n1 xy is equal to the way you do, right? Say alpha 1 plus beta 1x plus gamma 1y plus delta 1 xy. You will assume like that. And then you solve it, right? As in general we have done for for triangulars. So same way you do, you then find out basically. So basically in I xy in general, you say alpha I plus beta I x plus gamma I y plus delta I xy. Yeah, so you can do that way. However, when it comes to integrate, then you will face a problem. Then you have to anyway transform to this kind of shape in order to do the numerical integration. Because you want to finally apply the Gauss quadrature, right? And for that, you know that Gauss quadrature in 1D, we have done like something like this. So in order to find out this, I equal to f xi, v xi. For this one, you know it's equal to WIF, right? Xi I, and then I equal to 1 to number of Gauss points you did, right? So converting from -1 to 1, in order to integrate it, you will have to convert from here to here, and here you will have -1, -1, right? 1, -1, 1, 1, and here you will have -1, 1. Anyway, you have to convert that so that you can do numerical integration. Right? Well, if it is just simple integration, you can do it, but when it comes to f, which is complicated, finally this it gives you better. It has some advantage. You becomes faster and all. Remember that you are working with finite element analysis of aircraft or ships, which may have lakhs, if not millions of elements, right? And then in that case, you will face problem, because if you save a little bit of time, that accumulates and becomes a big time, right? So that's why isoparametric element in that way it helps. That way, you formulate that way. I mean, in computer, it doesn't know even what you are doing. You choose this or automatically transform this and this, because derivation becomes easier. So that's fine. So any question, guys? So this is one way of doing. Rest you know the drill. Yeah. Now what we want to do is we want to convert here to here, and then we want to do it. So if you convert, then we can write like this. We can have. We will define n1, n2, n3 in xi and eta now. That's what we will do. So we'll say n I. So this one becomes this one, here becomes 2, this becomes 3, this becomes 4. So we have converted that. So this one is just to tell you that there is other method also, a very standard method that you can follow. However, we are trying to know what is isoparametric element, and this we can also apply to triangular element as well later on. Okay, so Ni xi eta. Now you look at here. Now it's simple, right? As you know, we can write is equal to 1. Now we are talking about this one, so you know that this will be 1 minus what? Xi over 2, right? Length is 2, so xi over 2 multiplied by 1 minus eta over 2, because this is also a length of height is also 2. So n1 is given like this. Agreed? Basically, no, it's not 1. I can understand many of you were confused why it was there. So this is n1 we're talking about, right? So this is n1. Now n2 xi eta will be equal to, so we're talking about this one. So this becomes xi over 2, 1 minus eta over 2. N3 xi eta is equal to xi over 2, eta over 2. And N4 xi eta is equal to, we will have 1 minus xi over 2, eta over 2. So we have that. Okay. Now next. Okay, now this given like this. Now transformation is there. We have to now relate between XY system and xy eta system, right? That's very important, otherwise we will not able to do it, right? So relation between X, Y, and xy eta systems. And what relation we have? We can write simply X as xy eta. So define X itself. It is equal to Ni xy eta multiplied by X. I is equal to 1, 2, 4. Got it? So we are using the shape function itself to construct our X now, right? Because we know the coordinates. So we can construct like this. And similarly, you have Y xy eta is equal to summation, let's write J, after those, equal to 1, 2, 4, N J xy eta and Yi. Right? You can do it, and this is how you have constructed. So that means the relationship between the two is now defined. Now you can go ahead and you can do your analysis. Yeah. Remember that the basic rule doesn't change. That K is equal to a small k VTB d omega. It doesn't change. We still have the same thing. Only thing is now for this system, what is the value of B? Once we know B, and find out. So now next deal is finding out the value of B. So what is B? If you find out B, the rest is easy. Okay. Now B, as you know, that this is also 4-noded. The earlier element was also 4-noded. So this will have same number of members, 2 by 4, and you know that in this will be del n1 over del x, del n2 over del x, and so on, right? Del n3 over del x, del n4 over del x, del n1 over del y, del n2 over del y, del n3 over del y, and del n4 over del y. Only thing is, we have defined n in terms of xi and eta. That's the only thing. Yeah. So how to do it? Okay. Okay. So let's look at, in general, if you del ni over del x, that we will not write that way. We will write, we are going to del ni over del xi will be equal to, now n, you write del, what we want to find out, what is the partial derivative of n1 in terms of x, given that we know that n is a function of xi and eta, and there is a relationship between x and xy and xi eta system. So we will write del ni over del x, then del x over del xi, plus del ni over del y multiplied by del y over del xi. This you must have done already in some courses. Yeah. Okay, that's why we put a lot of mathematics courses, so you don't face problems. Yeah, I don't know how much it helped you guys, but I'm talking about the undergrads. For masters also, we have actually engineering mathematics and numerical methods. So del n, by the way, your old curriculum had like one compulsory mathematics, second was an optional, so something like that. Del n I del eta is equal to del ni over del x over del eta plus del ni over del y and del y over del eta. Time. 5 more minutes. Okay, so we can write like this. So that really means del ni over del xi, del ni over del eta is equal to, right? Is equal to, and you have here, which will be del x over del xi, del y over del xi, del x over del eta, del y over del eta. And then you have here del ni over del x, del ni over del y. Yeah. Do you recognize what this is? Jacobian. This is called Jacobian matrix. Okay. And then we have del ni over del x, del ni over del y is equal to, we invert that, right? So this is the relationship we have already. We have from here, right? We can find out what that is. Yeah. So we can find out, but here it will be, this is a very standard, basically we can find out, we will see that. So what you have is del x over del xi, or let's write just Jacobian inverse. Why to write? Already I said j, so we will have j inverse. Then you have del ni over del xi, del ni over del eta. Right? Once you find out, integrate it. Right? Now j we can find out further, and what we see here, that del x over del xi is equal to what? See here, equal to this. So this will be I equal to 1 to 4 del ni over del xi, right? Xi. Right? Differentiated this, right? Simply. And similarly, like there will be 4 differentiation. For this, you have del x over del xi, del x over del eta, del y over del xi, del y over del eta, and then you find out, and so on, right? So here, del x over del eta is equal to summation of del I over del eta del xi. Yeah. So del y over del xi is equal to summation of j equal to 1 to 4 here, and we have del nj over del xi yj, and del y over del eta is equal to j equal to 1 to 4 del nj over del eta you have defined already. These things are known, right? These things are known. Only thing is you will get the value of this. You will get value of this, but in terms of xi and eta only. But doesn't matter if it is in terms of xi and eta. We will just integrate in terms of xi and eta. We have to just find out the way that what is the equivalent of equivalent integration, and then we can do it. Right? So only thing is finding the equivalent. This is in terms of xy. Right now it is domain. Our domain is right now this xy system. This is omega, which is in xy system right now. We have to find out how to integrate the same thing in this system. Okay, that we will do tomorrow. Okay, and that will also follow that how to apply Gauss quadrature in this. Yeah, that also. So equivalent integration. Okay, or rather just integration using xi-eta system. That's what we have to learn. Otherwise, everything is covered already. Right? So we have del n I over del x in terms of xi-eta, and now we have to use. We want to know that how something which is given in xi-eta system we can integrate such a way. The way it should be in xy system, we should get exactly the same value. That's the right. So that we will do tomorrow. Any question, guys? Okay. I hope you guys are understanding that. Yeah. So in case of any problem, just let me know. It's very important, you know. So in fact, I like when you ask. No, so that really means that you are clapping. Means you are understanding at least. Okay. So Sanjay, okay guys, see you tomorrow.